Sorry about the interruption. I got a phone call. I had to decline it and it ended my video. Okay, so observed, expected, and then you subtract the two. So observed minus expected. So 691 minus 817, negative 126, positive 126. So you won't always get exactly the same numbers, but they'll be kind of similar. So just, you know, this is the fact that these you're the 120. Well, I mean, if you think about it, men first and men non-first, they're always going to add up. They're always going to be equal because it's like there's only so many men in the sample. If you expect them to be in the first, then you take away from what you expect in the second. So in a 2x2 table, these numbers will be identical. In a 3x2 or a 2x3 or anything above 2x2, they won't necessarily be, but it's a zero-sum game. I mean, you think about it, it's like if we observe this many men, but we expect this many, well, where did this expected come from? They come from what we observed with the non-first, because that's the only other place they could be. So in a 2x2 table, these numbers will be identical. The F observed minus F expected. Okay, so we take the difference, negative 126, and then 1259 minus 1132.86. You get the difference. So all we're doing here is just subtracting the observed number minus the expected number. And then similarly to, when we're calculating the standard deviation, you square the stuff to get rid of the negatives. That's sort of the, kind of the point is, we want to, because otherwise, I mean, look at this. What would all of these sum up to 0? Okay, so you got the F observed minus F expected, and then you square it. So negative 126.14 squared is going to be 15,911.2996. And again, you don't need to include all those decimal points. I caution you to don't truncate your decimals too soon, but 2 decimal points is fine usually. But just I'm not going to be super strict on that, but just make sure you're not rounding too early. But again, if you want to round this to 15,911.3, that's okay. Okay. All right, so the numbers that won't be the same are so I have the observed minus expected squared, and then I take this number and divide by the frequency, the expected frequency. So here I'm dividing by 817.14. So let me just do that. So 15,911.2996. 15,911. Right, so that's your observed minus expected squared for men first. And then we divide it by the expected number of men first. It's going to be 817.14. So divided by, by 817.14. 19.47. Oops. And there you are right there. So then for men, non-first, you take this 15,911.2996 and divide by the expected number of men non-first, 1,132.86. You get 0.05. Women first, it's the same thing. So if you need any extra help with this, I can do another example. And I think, you know what I'll do? On Thursday, I'll give you another example of this, and I'll work it out on the paper. But just, I just want to be as consistent with the book because, that's the stuff that you're seeing worked out. So hopefully hopefully it's helpful. But yeah, it's really going to be the same thing every time where you just, so here's all your combinations. It's not really gender as much as it is sex and first-generation college students and men first, non-first, right? And then you're observed, you're expected, then you subtract the two, then you square them, then you divide it by the expected, and then you sum them all up, because remember, the original equation is the sum of all this business. So we take 1947, 1405, 1422, 10.26, add them all up and get 58, okay? So that's your chi-squared value. So here's the fun thing about chi-squared is it's, like I said, it has its own sampling distribution. So the sampling distribution of chi-squared tells us the probability of getting values of chi-squared assuming no relationship exists in the population. So think about that. It tells you the probability of getting a certain value of chi-squared assuming there's no relationship in the population. So we got a value of 58. We want to know what's the probability of getting that 58 when in fact there is no relationship. So again, it's going to be based on a confidence level. It's going to be based on that same, we calculated our test statistic. We're going to compare it to a cutoff value. Same thing as, same determination that we did before with the hypothesis testing. It's still calculated test statistic, compare it to a cutoff value. In this case, it's going to be a chi-squared value because in chi-squared testing, we use the chi-squared sampling distribution. So just like the t, the chi-squared is this family of distributions, and it's dependent on the degrees of freedom. So a couple things about the distributions themselves. They're positively skewed. They're always greater than 1. And as the number of degrees of freedom increases, the chi-squared distribution approaches normality. So take a look here. Like I said, it's a family of curves similar to the t. So if you think about it, the z distribution is the least flexible. It's the most rigid. Z distributions are always normal. They don't change. It's the same every time. The t distribution, depending on the degrees of freedom, it had more variability, right? The curve was either flatter or steeper or more normal depending on the number of degrees of freedom. The chi-squared distribution is similar to that, but it doesn't even necessarily have to be it doesn't necessarily have to be like normal or approaching normal at all. It could be highly skewed. And if you take a look, a degree of freedom of 1 is almost like, it's almost unrecognizable. It's extremely skewed. Degree of freedom of 5 and 9, these are skewed more. Once you approach 30, like I said, it becomes more normal. But just know that, and this is in your book, just know that this is a different distribution and it's the most flexible. So Z is the least, T is kind of the middle, the tweener, and then the chi-squared distribution is the most flexible. So the degrees of freedom calculation is a little bit different. It's not more difficult, it's just a little bit different. So the way it's done is you take the rows -1 times the columns -1, okay? So in this case, it's easy. We have two, and these are, so the number of rows is going to correspond to the attributes. So we had men and women. Those were the column variables. Obviously, that's our independent variable, men and women. And then our row variables were first and non-first in college. So we have two row attributes, 2 column attributes. So 2 minus 1 times 2 minus 1 is going to be 1 times 1, which is 1. So your distribution is going to look like this highly skewed one here, which doesn't look anything like a normal distribution at all. Again, the chi-squared distribution is much more flexible. Okay? Then the easy part is the decision. So the chi-squared table's in Appendix D. I'll get down here. So here's B, our standard normal table. This is the Z stuff, very rigid. The T distribution, again, dependent on the degrees of freedom, much more flexible. And then you have the most flexible of them all, the chi-squared distribution in Appendix D. So here's how you make the decision. We had 1 degree of freedom, right? And across the top, what you have are the different confidence levels. So I don't know why you'd only want to be 1% confident, or, this would, so, 0.99 would be, basically like it would be, we'd leave it up to chance 99% of the time, where 0.99 is the proportion. 0.01 would be the proportion of certainty, which would be 1%. I don't know why you'd want to use that, but I guess it's there if you'd like it. The point is that we want to focus more down here. So with the chi-squared test, it's interesting. I can give you an alpha cutoff level, or you can determine it on your own. Similar to, I hope you've realized that like in the T and the Z, like in the hypothesis testing before, I can give you a cutoff level to test it, but you can kind of look and see yourself and say, well, I am confident at this level, but not at this, or, I'm confident at the 99% level. So you sort of have the flexibility. Hopefully you're kind of catching on to that, but at least for the sake of the homework and the exams, I'm going to give you a cutoff level. So let's say I wanted to be, let's say I wanted to use an alpha of 0.05, which would be 99% confidence level. Well, you've got a cutoff value of 3.81 there. If your chi-squared value is greater than the cutoff value, then you can be sure that the sampling distribution, where am I? Lost my place. So basically it's telling you that if, let's just keep it simple. Just like the T test, if your test statistic, so the number you calculated, 58, is greater than the critical value, then you reject the null. You go with the research. So if you look here, though, I could have said tested at an alpha equals 0.001, which would be a 99.9% confidence level. Well, we're still above this number, so we're still saying reject the null. So our decision here, going back to the hypothesis, we would reject the null, and we would say we can be sure with 99.9% confidence that there is a relationship between sex and generation of college students. And if you look, I make the decision and interpret the results. So that's the first bit is, you made the decision, you're going to reject the null, you accept the research, and you're going to say that there is a relationship. But the interpretation part is a little bit more, there's a little bit more to do there, because you've tested, you found a relationship, you know that there's a statistical relationship between these two variables, but now you want to tell me what it is. That's fine that there's a relationship between sex and generation of college students, but how? So that's going back here where you saw that there's a greater proportion of men who are non-first than women who are non-first. So then you can apply that to your sociology. Why would there be more women first-generation college students than men first-generation college students? I don't know. That's a good question. It could educational differences in the past. We know that more women are attending college now than any time in history. In fact, there's more, higher enrollment of women in college than men, in fact. So your first thing is you've told me with 99.9% certainty. You could say 95, but why not bump it up, because the 50 is still above this number with 1 degree of freedom. So you can tell me that you are 99.9% confident that there is a relationship between sex and generation in college, and that it operates in such a way that there are more first-generation women than first-generation men, and there's more non-first-generation men than there are non-first-generation women. And then explain why you think that might be the case, but that would be the interpretation bit of it. So that's all I'm going to do for today. And if you go back to the first slides here, we answered this question. Is there a relationship? Yes. What I want to do on Thursday is work out another problem for you, like do another example, and then I want to look at these next two issues. How strong is it, and what's the direction? So we know that there's a relationship. I'm 99.9% sure that there is one. And we've described how it works. It operates that there's more first generation women than men, and there's more non-first generation men than women. So there is a relationship. We're sure that it's significant. The question is, how strong is it? Is it a strong relationship? Is it moderate? Is it weak? Is it, how is it how can we assess like how robust the relationship is? And then lastly, what's the direction? Again, we're going to do this on Thursday. Give this a little time to let it settle. Sorry for having to break up the video in a few different sections. I had a couple interruptions with the dogs and a phone call, so such is the nature of things with the online stuff. So anyway, let this kind of ruminate. Read the chapter, please, chapter 11, and I'll post your assignment for you after the second series of this, so part 2 of the chi-squared testing. But I think, I think as long as you're organized, this is, again, I'm going to just re-emphasize, make sure you're writing everything down and staying organized. It's really easy to get some of these numbers mixed up. But if you write things down sequentially, you'll be able to check, are my observed marginals the same as my expected marginals? If they're not, you made a mistake. If they are, then you're good to go. And you get down here, and this is where you really want to stay organized, because we want to find this. Here's the equation for our chi-squared, but similar to the standard deviation, we've got to build it in pieces. And again, your book does this too. So check that out. Let this kind of settle in, and then I'll have a homework assignment for you, which will be, pretty much nothing super abnormal. I think what I'll do on Thursday is work out so this was a 2x2 table. Let's work out like a 3x2 or a 2x3 or something, so it's not, a zero-sum thing like I, gave you where the numbers, are the same here, just so you can see a different example. So that's all. Good luck, and as always, let me know if you have any questions or need to go over anything, but keep it up. We're getting through almost to the end, so keep up the hard work. Bye.